So concept map of Z transform. So we all know Z transform is a transform from time domain to complex frequency domain for discrete time signal only. Xn is the discrete time signal. We can get Xn from xt by sampling xt from continuous time signal. Here we represent Z transform as Xz. In polar form, Z equal to R e to the power j omega. R is the radius of the complex Z plane and omega is the angular frequency. If we put R equal to 1, then we get DTFT, discrete time Fourier transform. We can also find DTFT from Xn directly. We can directly find DTFT from a discrete time signal, that is Xn, and if we put to the power minus n in DTFT, then we will get Z transform. Here we will see the omega is the angular frequency, and if we put omega equal to 2 pi by n into k, then we will get DFT, discrete Fourier transform. So here is the formula of DFT. Xk will be your summation of n equal to 0 to n minus 1 xn e to the power minus j, and here in place of omega we will put 2 pi by n into k. So we will get DFT for a complete period of that DTFT. And if we find DFT of a impulse signal, that is denoted as Hn, then it will represent at Hk, and if we multiply it by Hk with Xk, then we will get Yk, which is the normal multiplication in frequency domain. And if we find IDFT of Yk, then we will get Yn, which is the time domain convolution of Xn and Hn. That's why the analysis and synthesis are much easy in frequency domain rather than time domain. And here we will see for continuous time signal xt, we can find CTFT, continuous time Fourier transform, which is represented as capital X of j omega. Omega is represented for the continuous time signal, and if we multiply it e to the power minus sigma t with CTFT, then we will get your Laplace transform, which is represented by x's, and we can directly find Laplace transform from continuous time signal of a continuous time signal, which is represented as x is, and if we put sigma equal to 0, that means s equal to sigma plus j omega, and if we put sigma equal to 0, then only j omega will remain, and it will become continuous time Fourier transform x of j omega. So Laplace transform is a generalization of CTFT. That means in case of CTFT we are only limited in j omega axis, but in case of Laplace transform we will go sigma and minus sigma, and it is quite similar for Z transform, which is the generalization of DTFT. In case of DTFT, the radius is limited at r equal to 1, and if we remove the boundation, and if we go for entire complex plane, then we will get a new transform, that is called Z transform. So if we put r equal to 1 in case of a Z transform, then we will get DTFT. So here, suppose in similar way, suppose we find out a transform of that HN, which is the impulse response, we will get HZ, and if we multiply it with HZ with XZ, then we will get YZ, and if we find inverse Z transform, then we will get YN, which is the time domain convolution.